Well, Emily, it could just be you and me.
Okay.
Sorry if you said something I was muted there for a second.
Oh, that's okay. I just said that's whatever.
Um, so we'll just wait another second to see if anybody else joins. It's usually better if we have a number of people to sort of have more of a dialogue. Even if people are rewatching it, it's a little bit better, but
Yeah.
we'll see. If not, then it's your own private kind of study session with the author of the test, which is not a bad thing.
Yeah, because I don't even have a ton of questions. It's more I just wanted to see everything again.
Well, and that's why usually it's helpful if there's a number of people there. My plan was, is it, depending, and that's not uncommon where people don't have questions, but I'll just kind of take an opportunity to make sure that I go through the study guide and just kind of make sure that it's clear what I'm asking in the study guide, because sometimes that can be confusing. I'm sitting here looking at the Siri, I'm not talking to you. I'm looking at the test and it's like, trying to make sure, yep, that part's on the study guide, that part's on the study guide, like that I'm not asking you something that's not on the study guide.
Uh-huh.
So why don't you go ahead and ask me what your questions are first, and then I can kind of take more of a sort of generalized approach to.
Well, I am pulling up the study guide right now from Blackboard. But
Okay. So here, let me go ahead and I'm going to do this. I'm just going to share my screen and then I can pull this up in Blackboard so that whoever is maybe watching this later can also sort of see what we may be talking about.
Okay, also, just so you know, I did have trouble getting in. I had to like copy the link and put it into my browser, so I don't know, maybe people are
Okay. So let's see. Oh, I was just actually, while you're here, I was just about to send you a message on Teams. Do you know what the email is that you use to sign in to your ring? Because that's the latest things. They keep coming back to me and they're telling me your ring's working fine. It's been charged for like 5 days. I'm like, yes, because you're looking at my aparenti@Mercyhurst email. It's not the right ring.
Will my app tell me? Because I don't know.
I don't know. It might be. What size is your ring? Do you know?
The one that works?
The one that works is an 8, right?
It's an 8, and you said that it was one of the older ones.
So my guess is, I think it's chem331 aura8@gmail.com. So
I honestly don't remember.
That should be it, because if it's one of the old rings, I only had one of each size. And so when I set up emails, the email was the size of the ring. So it was like Aura 8, Aura 7, Aura 11, because I only had one of each size. So I'm pretty sure that's it. So I wanted to confirm the ring size with you. Okay, so what I had wanted to do, so I sent you that message just as a reminder to myself. So I put it in there. Let's see. Yeah, because I think it's strange that no one else is here. Is there anybody else?
What'd you say?
I was just saying, did you know anybody else that was planning on coming that they're not here?
I'm not really friends with anybody in the class, so I haven't talked to anybody.
Okay. I'm just going to send a quick message out. It's frustrating, like all these Zoom things get in the way. Okay. So going to make this high priority. Review session starting now. And please send me a message on Teams if you are having next meeting session. Right. All right. All right, so I'm just going to come back here, and what questions did you say you
I just
had?
kind of wanted to see everything again, kind of like I have all the notes and everything, but I guess I just don't know, like, I guess what type of questions you were gonna ask.
So how about we do this? I'm going to go through, and just to highlight for everybody, if people are watching later, here's where you can find different things. So under the exam preparation tab is where you'll find all the study guides for the exams. So if I open up kind of exam 1 study guide, it kind of highlights some things that you need to know. You need to know qualitatively about acid-base equilibria. So what does it mean to be an acid? What does it mean to be a base? You know, if you had to write our basic fuel equations or the 2 equations that we have that are part of our blood buffering system. And I'll kind of go through those. I'll kind of flip through our slides as well. I posted. I found this on the equations that we have that are part of our blood buffering. Oh gosh, Siri thinks I'm talking. No, I'm not talking to you, Siri. And our breathing equation. So this kind of all comes together with that one homework question that you have too. And you know, talking about homework could be helpful too. Quantitatively be able to use the Henderson-Hasselbalch equation. So, you know, that's an equation you need to know and know how to use it. There was a couple of homework problems that kind of related to that, so we can sort of look at those too. In the aspirin overdose case study, we used the Henderson-Hasselbalch equation to sort of explain solubility with our aspirin, and then blood pH when we talked about sort of the ratio of carbonic acid and bicarbonate. And then free energy, there's 2 equations you need to know for free energy. Delta G equals delta H minus T delta S, and then delta G equals minus RT ln of K. So I'm going to pause there for a minute and see if you have any questions on any of that.
When you say knowing if something's an acid or a base, is that like looking at like a drawn out structure, or if you give us like obviously like OH minus or like H3O plus, something like that?
Yeah, well, and it's also sort of relating to, I'm trying to see here, like if this idea, like relationship between pH and pKa. If I were to give you a structure of something that has functional groups that you know, and you know the pKa value of, tell me what the protonation state is of that molecule. So that's related to like homework question number 1.
Okay.
Right? So again, I wouldn't expect you to know those structures, but if you are given a structure that has functional groups that you know, be able to draw me what that molecule looks like under a given pH. Does that make sense?
Yeah.
So that's kind of relating to sort of this acid-base equilibria, and just being able to think about, and what does a weak acid do in water? Well, it partially dissociates into H plus and A minus. What does a weak base do in water? Well, it finds water and it takes a proton off of water. Siri, what? Leaving behind hydroxide, which is why bases increase pH, because they increase the OH minus concentration.
Okay. Can we do an example problem for that?
For like the protonation state one or the
protonation state, like
oh, what are you all worked up about? There's nobody here. Come sit. Come. Lay down. You lay down. I know you're trying to protect Mama, but here. There's Charlotte. She's trying to protect Mama. There's nobody here. Let's see. I'm trying to think about the best way to kind of pull up something to sort of show you. Let me see if I can connect my iPad here. So let's try this. I'm going to try to log in using that same Zoom link so that I can connect. I have to stop sharing here. So did you do the, let me just ask this, did you do the first homework question?
No, I have not done them yet.
Okay, which is okay. I mean, it's only Tuesday,
Yeah.
but that's why I wanted to do things early. So that might be a good thing for us to take a look at. So why am I not? Why is it asking me to get codes? I guess I need to log in here. Oh. It's probably going to need a text authentication. So frustrating. Like, I don't know how many times you have to sort of log into things with like that two-factor authentication.
Oh, yeah, my authenticator app doesn't work. Or you mean like with your phone number?
Well, like if I'm logging in, it'll send me like the 6-digit code.
Yeah.
All right, so I'm in now. So let's see. Just trying to get to this link. It's not the right one. Here we go. All right. Got it. No audio. Okay. Share content. Share screen. All right, so you should be able to hopefully see my iPad screen now. I need to just go grab my Apple Pencil.
Okay.
Because it is downstairs. But let's see, what I'm going to do is pull up. Let's see. I'm going to want to pull up. I didn't go through homework with you guys this year, but I think I did last year. So let's see. Well, I didn't. But I can do this. We'll do this. We'll actually do that homework problem. I think I have homework problems sort of embedded in here, but we didn't necessarily do them in class. Here we go. So let me go grab my Apple Pencil and then we'll go through this problem and that hopefully will be a way to sort of talk about it. Why don't you, while I'm going to get my pencil, try to look up these structures on like Wikipedia.
Okay.
And yeah. Oh my gosh, she's so funny. All she does is follow me around. All right, let's see. All right, so here's some of the things that you should be getting from the structures of these. So pKa for pyruvate is 2.50. If I draw the structure of pyruvate, it's what we call an alpha keto acid. So that's the structure of pyruvate.
Okay.
Right? It's CH3, C double bond O, COOH is what it is. So I'm just drawing it as a skeletal structure.
Okay.
Good so far?
Yes, I had that as well.
Okay. So if we're looking at figuring out protonation state, and actually I drew the correct protonation state for this guy, but the only reason that that is the protonation state is the pKa of the molecule is 2.5. In the stomach, where the pH is 2, we are below the pKa. Remember, bigger number wins. So if the pKa wins, pKa is a property of the molecule. So that means the molecule gets to keep the proton. So part of what we need to do here, and this is part of sort of this acid-base kind of things, is there's hydrogen atoms here in this molecule and here. But it's important that you be able to look at the structure of a molecule and understand what hydrogen atoms are acidic. And they're always going to be ones that are connected to heteroatoms, such as oxygen, nitrogen, potentially sulfur, right? But mostly oxygen and nitrogen. Okay, does that make sense? So now if we move up to physiological pH, I'm going to have you tell me the answer. Who wins, environment or molecule?
Hold 1 second. Sorry.
It's okay.
The pKa would win.
Well, careful. pKa is always 2.5. Bigger number wins. When we're
sorry, I wrote 7.4, but yeah, the environment wins.
The environment wins. So when the environment wins, it takes the proton off, and so we draw this molecule in the deprotonated state. So we draw it like that.
Okay.
Okay. So that's protonation state. Is, well, first of all, from the acid base sort of piece, we need to understand that we need to identify which hydrogen atoms are acidic. And then using what we know about either pKa values that are given, like we have in this homework problem, or if you were to see a hypothetical molecule where you saw things like carboxylic acids, protonated amines, or alcohols, you should be able to do this same kind of pH pKa comparison to determine what's the proper protonation state.
Okay,
so go ahead.
Sorry. If something, let's just say something had, so if there's like one carboxylic acid, does that mean that the whole molecule was that 3 to 5? Does that mean that the whole molecule is like in there?
So that's a good question, because if you start decorating something with like multiple carboxylate groups, it's interesting because the first one will have a pKa value of around 3 to 5, but once that guy loses its proton, it actually increases the pKa of the next one, only because to put two negative charges close to one another is sort of unfavorable. So that's getting a little bit tricky. Okay. But a good question. But in general, I want you to sort of just play the thought process that a carboxylic acid is going to be 3 to 5, and then just do the numbers game.
Okay. So we won't have any that are like let's just say a carboxylic and an amine in the same molecule. Will it just?
No, you absolutely could. That's an amino acid, right? But you would need to say, okay, the amine in its protonated form has a pKa of 9 to 10. The carboxylic acid has a pKa of 3 to 5. So depending on what the environment is, that's going to dictate what both of those do. So absolutely, it's fair game to have multiple what's the word I'm looking for? Chart or pKa values.
Okay, so would each of those groups then do something different? Like let's say it was 7.4, so then the
amine. So let's do that. Yep. So let's do an example. A perfect example of something that contains both of those is an amino acid, right? Because an amino acid has an amine group and a carboxylic acid group. And if you go ahead and you look up, for example, amine or carboxylic acids on Wikipedia, it's going to frustrate the heck out of me because you're going to see structures that look like this. Because there's no way that any amino acid will ever be uncharged. And that's because if we are basic enough that we've deprotonated a protonated amine, we're certainly going to be deprotonating a carboxylic acid. Okay, so this is something that kind of is hypothetical. So we're going to kind of highlight that we would never have this. So let's reconcile and show what this structure really would look like. Okay, so one of the ways that you could do this is say, all right, let's imagine the pKa of 2 situation. Well, we know the pKa of a protonated amine is going to be 9 to 10. And then when we consider the carboxylic acid, and let's keep that in its protonated state where we know the pKa of that, the pKa of that is 3 to 5. Oh, Charlotte. Okay. So this would be, let's say, the protonation state of this amino acid at pH 2. Because in that case, both pKa values are going to win. They're above the pH of 2. And so everybody gets to keep their proton. And I was talking to Lauren about this today when she was in my office, right? And the idea is we're talking about one of those protons. I don't know if how well you can see that color. It's kind of a little washed out on my screen here.
I can see it.
All right, I'm just going to put it in blue so it's a little bit darker there. Okay, when we're talking about those protons, when we're talking about the pKa of 3 to 5 or the pKa of 9 to 10, those are the ones that we're talking about. And if the molecule wins, it keeps that proton. But if we start to go to, let's say, physiological pH, okay, so this is going to be pH 2.0. If we go to pH 7.4, we have not yet gotten basic enough to deprotonate the amine group, but we have gotten basic enough to deprotonate the carboxylic acid. So that's what this guy is going to look like at physiological pH. Does that make sense?
Yes, it does. Thank you.
And so the idea is this molecule has, and we're going to get into these weeds a little bit more. You don't need to know this sort of detail, but just to give you a preview, this molecule is what we call a Zwitter ion. It's a molecule that has no net charge, but it is not uncharged.
Okay.
Okay. Does that make sense? Like the net of this is that the +1 and the -1 cancel each other out.
Yeah.
So it has no net charge, but it's not uncharged. This molecule over here is technically uncharged, but it's also it's not possible, right? Because you're never going to have this guy be deprotonated and that guy be protonated. Make sense?
Yes, it does.
All right. I don't want to get too much in the weeds with one problem, but that's kind of how this homework problem is set up. Look up the structure of imidazole and then look up the structure of 2,4-dinitrophenol. These are all molecules that we're going to see at some point in the course. So it's worth kind of thinking about what they look like.
Okay.
Let me go back to, let me stop sharing here. And I'm going to come back to sharing my screen here so we can go back to our study guide. Okay, do you see the study guide again?
Mm-hmm.
So thinking about numbers to know, we just kind of went through thinking about those 3 functional group and pKa values. Know the pKa of carbonic acid.
Okay.
We use that in our kind of blood buffering system set of equations. No physiological values. So physiological temperature is 37. Physiological pH is 7.4. Net worth for ATP is 30.5 kilojoules per mole. We talked a little bit about eukaryotes and prokaryotes, and it's not specifically on this study guide, but if you had to give an example of a prokaryote or an example of a eukaryote, we talked about some prototypical prokaryotes are like E. coli. We really haven't talked about any other bacteria. And there's lots of other things that would be sort of a model eukaryote, everything from yeast to fruit flies, to worms, to mice, to humans, right? Those are all kind of model eukaryotes. We talked about kind of protonation state, the relationship between pH and pKa. Intermolecular forces, be able to name and rank those intermolecular forces. So do you remember what the 4 intermolecular forces are?
London dispersion,
Yep.
dipole,
Mhm.
hydrogen bonding,
Mhm.
and I don't know what the fourth one is.
Ionic, also called
Okay.
electrostatic. Yep. And you actually gave them in the order from weakest to strongest. So that's perfect.
Okay.
Be able to define the hydrophobic effect. Do you remember what the hydrophobic effect is? The tendency of nonpolar substances to minimize their contact with water. Okay, that's listed like right in the notes. So to highlight here, if you want to go find, and we can even open this up now. If you go under learning units and under this unit 1 folder, I'm going to open this in a second. So here's my annotated notes, which includes stuff from the case study right here. And highlighting too, I put 3 new videos up in the past couple of days here, just some of the slides that we had in class that were maybe a little bit more like storyboard like slides. So there's one on the blood buffering system. There's one on thermodynamics, and then there's one on reaction coordinates. So if those are things you feel like you want a little review, this one's a little bit longer because I go through both a regular reaction coordinate and then the one for ATP. But they're ones that if you feel like you need a little review, you can. But let's go ahead and open this up. So this is just my copy of notes. Apparently it's going to take a little while to open. I'll come back to that in a second. I think I was going to show you where that definition of the hydrophobic effect is. So obviously you don't need stuff in the beginning there. I just copied everything.
Quick question while you're finding that.
Yeah.
So for the thermodynamics, is that gonna be a lot about like the spontaneity of
So let's get to those slides, and we can sort of talk about it. So okay, this is an important slide, which is why I have a separate video on it. You should be able to, for the thermodynamic parameters of free energy, enthalpy, and entropy, since you do need to know this equation, you should be able to identify which letter corresponds to each parameter. Talk about in words like what do we mean when we talk about enthalpy? What do we really mean? Well, we're talking about bonds, intermolecular forces, or interactions. Which situation is favorable? Do you want enthalpy to be negative or positive to be favorable? So almost like thinking about taking this information and just sort of like putting it, it's kind of in a grid already here, but simply being able to say what letter corresponds to each word. What's the short phrase that I told you to think about with it? Like here's like in one word, we can define entropy as disorder, but a phrase is more molecules moving more. For free energy, like the one word is spontaneity, right? And it's favorable if it's negative. So be able to think about that. And then if you were to be given some examples of like win-lose or win-win situations where you sort of had to tell me, like, is this reaction always spontaneous, never spontaneous, spontaneous above a certain temperature or below a certain temperature, depending on sort of, that's kind of like this sort of scenario. If you were to be given some examples, sort of be able to tell me, hey, given this set of circumstances, is this reaction spontaneous, not spontaneous, spontaneous, above a certain temperature type deal. So if you want if you feel like you need a little review with that, again, there is this video right here that kind of walks through that slide again, about 9 minutes just on thermodynamics. All right. So be able to think about some aspects of what we did with the aspirin overdose case study. So not necessarily like regurgitating and spitting back facts, but like understanding how pH relates to solubility. And talking about how we can use the Henderson-Hasselbalch equation to think about solubility. You do need to know the Henderson-Hasselbalch equation. I do need you to know how you make a buffer. Tell me what you use to make a buffer. What two things make up a buffer?
I don't know.
Weak acid and its conjugate base.
Okay.
Right? So if you want to have a buffer, you have to have a weak acid and its conjugate base. You can't just have like a weak acid and some random conjugate base. It has to be a matched set. Okay. There was a homework question, and we can even just pull up the homework here just so that we could point to these questions. So as we're looking at homework, we've kind of talked about some of these pieces already. Homework is going to be a really good prep for kind of practicing some of the problems. So this one practices pKa, pH, and protonation state. This problem, if you were to say be given a table of pKa values, which one is going to be the best buffer to choose for this? And again, you're going to want to sort of match your pH with the pKa of whatever acid that you want, right? So that's all that this one is. A couple of problems here that are calculation based, okay? Needing to use the Henderson-Hasselbalch equation, or problem 4 is a little bit more involved because you need to tell me how to make a buffer. So I'm going to highlight here a place that you can go for some help on that. And maybe what I'll actually even do, maybe it's not there. I will actually.
Is that what we did in lab?
It is what we did in lab, but a little bit simpler. We did it a little bit more in depth in lab, but that's why I'm going to the lab math section here. This video, I'm going to copy this over to our Blackboard course for the lecture. Oh boy, let's see. Where is, I need to find biochemistry fall 2022. There it is. Should have looked right above it. Okay, gonna put it in our intro unit. Okay, so now I should be able to find it over here. Just refresh. Okay, all the way down the bottom here, I'm going to put a little comment here, and I worked through this with Lauren today. So if you start at 16 minutes, you get help with buffer calculations. So that is, oh, I can't spell calculations. Calculations. Okay. So this is going to be, I'm going to just show you here. We start this.
End up with a number.
We started about 16.5 minutes, I think it is.
We have way more.
Maybe it's 17 minutes. But it walks through like preparing buffers, how to do the calculations for buffers. So it looks like it's actually maybe closer to 18 minutes, so maybe 17.5 minutes.
Okay.
And you know, there's only about 7 minutes total here, so it's not very long to watch, but that's going to be a really good kind of walkthrough in terms of how to do buffer calculations. So that's going to be homework question 4.
Okay.
Question so far?
No, I did think of one more unrelated.
Yep.
Are we going to have to do mechanisms?
There is a mechanism that's on there. Yep. There's one mechanism that's on there. It is something, so the whole test is, I think, worth 100 points. So it's a 7-point question. So not a ton, but not trivial. But what you want to do, and this is something, let me see, this could be helpful. I'm going to share a few slides here. or I took a picture of the board as I was working through this with, let's see, I think it was Jimmy and Skylar. So I'm going to just airdrop these to my computer here, and I'll open up these pictures and kind of do a little quick mechanism review, because it seemed like the most helpful thing that we were going to have was going to be not me going over each mechanism, because you already have videos to do that. And you're one of those people who watches them. What you need help with is, okay, it's something I haven't seen before. What do I do?
Yeah.
Okay. So just going to walk through. Can you see my pointer here?
Yes.
My cursor? Okay. So the key here is recognizing you have to find a nucleophile and you have to find an electrophile, because those are things that interact to do mechanisms. Those are things that interact to do chemistry. Okay. So how do you find things that are nucleophilic? Okay. Remembering that nucleophiles are where arrows start. So you're going to be looking for bonds or lone pairs of electrons, which are going to be on heteroatoms, such as oxygen or nitrogen. Okay. And so we're going to have things like OH groups or NH2 groups. So we're going to be looking for things like alcohols or amines to be our nucleophiles. Okay. Now, a theme that we're definitely going to see, and you've probably seen it, you know, if you've thought about the last 4 mechanisms that you've done, they are related to carbonyl containing chemistries. Okay. So carbonyls are great electrophiles. Now notice I didn't say a specific functional group, because there's lots of functional groups that have carbonyls, but a carbon doubly bonded to an oxygen is a great electrophile at the carbon atom, because if we draw a dipole arrow, that dipole arrow is going to point towards the more electronegative atom, indicating that that carbon atom is slightly positive, which makes it a great electrophile. Okay, so if you're struggling with mechanisms, one of the things that I want you to do is, after we have this, I'm going to talk for about 5 more minutes with my next picture here. Go and look at your 7 mechanisms that we've done so far. Okay, the first 3 were part of a set of 3 mechanisms that were related to one another. It had to do with a nitrogen atom on an amine as a nucleophile, and then either a carbonyl or a proton being electrophiles. So here in that first mechanism, all we did was acid-base chemistry. And that's because we always have to remember that protons are really good electrophiles too. So nucleophiles are also bases. So it's often easier for our nucleophile to just do acid-base chemistry if there's something that's acidic. Okay. And so that's what happened in reaction mechanism 1. And then once we got rid of that proton, because we didn't have a carboxylic acid functional group anymore, in reaction mechanism 2, we had an acid anhydride. And in reaction mechanism 3, we actually made a biological good leaving group with that OAMP group. Now, the only electrophile that was available was that carbonyl containing compound. Okay, so after we sort of talk about this, and after we're done sort of reviewing here, sometime in the next few days, go back and look at your mechanisms and see if you can look at arrows and recognize that they always start at electrons, either a bond or a lone pair. And they always go to atoms, which are electrophiles, either carbon atoms that are part of a carbonyl containing functional group, or, and our first mechanism is the only one that we sort of see this, a proton. Actually, I shouldn't say it's the only one we see this, because we do a good bit of protonation or deprotonation event. So we're certainly showing things where if we're having an arrow go towards a proton, that means we're protonating something, and we're forming a new bond to a proton. Good with me?
Yes.
All right. So then the next thing we sort of talked about was trying to identify sort of these patterns that we see. Okay. So the first 3 mechanisms that you did, it had a carbonyl containing functional group. Okay. And that carbonyl containing functional group, oh, it's just Sam. Hey, fine, go see who it is. Go protect Mom. Go see who it is. You're such a scaredy dog. So this X is going to be something that's a good living group. Hey, come here. You lay down. No, you lay down. You're fine. Sit. You stay. Oh my gosh. Fine, go downstairs. Go downstairs. So X is a good leaving group. She's worse than when I had kids. Hey, please. Hey, Sam. Sam. Oh, JT. Yeah, take her because I'm doing a review session right now and she's getting all freaked out because you hear the garage open.
Where's everyone?
Sam's at the volleyball game. Dad and David are still in Buffalo for practice.
I accidentally left my AirPods at school,
Oh, that's not good.
but I think it should be fine. They're all 10 minutes.
Okay. All right. Yeah, I got about another 20 minutes here, bud. Okay. All right. Now we're back. So when X is a good leaving group, X as a good leaving group could be a halogen. If you imagine this is a chlorine atom, this is what we call an acyl halide. We don't see molecules like that in biochemistry, but you did see them when you took organic chemistry. That's a good leaving group. Maybe something like this carboxylate group. If we had that group here in place of X, that would be a good leaving group. Okay. When we have chemistry where our electrophile is a carbonyl containing compound where X is a good leaving group, here's what happens. And I encourage you, if you're watching this now, or Emily, if you want to sort of pull it up now, Adam, I know you kind of joined us a little bit ago. Look at reaction mechanisms 2 and 3. So if you look at reaction mechanisms 2 and 3, here's the same pattern of what we have happening chemistry-wise. We've got nucleophilic attack, and we form a tetrahedral intermediate. Okay, I'll pull up a mechanism and I'll show you this in just a second. After we form that tetrahedral intermediate, we do some proton reshuffling, and then we decompose that tetrahedral intermediate, meaning we reform that carbonyl containing functional group, and we've essentially swapped out our leaving group for our incoming nucleophile. Okay, so I'm going to flip to a mechanism here just to kind of show you that. So let me kind of come back here. I'm going to open up a mechanism to show you that. Reaction mechanisms. Let's open up the second reaction mechanism. Okay, so I'm going to open up this PDF file so that we can kind of highlight. So I had said, while this is opening here, here's the pattern when we have a good leaving group. So X is going to be something that's a good leaving group. We see nucleophilic attack. We form a tetrahedral intermediate. We'll talk about why we do this proton reshuffling. We decompose that tetrahedral intermediate and we get our carbonyl back. Okay, so let's look at this mechanism now. Okay. So here's our carbonyl containing functional group. It's got a good leaving group that's here. This is a carboxylate group. How do you know if something's a good leaving group? If it is a weak/stable conjugate base, it's a good leaving group. I'm going to say that like 3 times because it's involved. If this is a stable conjugate base, a weak conjugate base, meaning it came from a stronger acid, this is the conjugate base of a carboxylic acid, which is it's a weak acid, but it's a fairly strong acid, meaning this is a stable conjugate base. Okay, so that's a good leaving group. That's how you identify if something's a good leaving group. So flipping back here just for a second, here's the pattern we're going to see. Nucleophilic attack, form a tetrahedral intermediate, do some proton reshuffling, and then decompose our tetrahedral intermediate, and then reform our carbonyl. So let's take a look at that here. Here's our nucleophilic attack. We can't have 5 bonds to carbon, which is why those electrons move up and we form a tetrahedral intermediate. Now, this tetrahedral intermediate, it could decompose. We could reform this carbonyl right here. But if we reform this carbonyl here, the best leaving group is still this guy. If you want something to be a good leaving group, protonate it. So that's why we need to do some proton reshuffling. We're going to take a proton off of here. Okay. It's not incorrect if you didn't protonate up here, but we do some proton shuffling so that this is no longer the best leaving group. Okay. And then we're going to get to where we decompose this tetrahedral intermediate. So decomposing a tetrahedral intermediate means we reform a bond between oxygen and carbon, a pi bond using a lone pair of electrons. And once we do that, again, we can't have 5 bonds to carbon, so something needs to break. Now, this is the best leaving group because we removed the proton from this amine. So this guy is going to be our leaving group. And if we look at what we started with compared to what we ended with, this is what we started with. This guy is our leaving group. We swapped out our leaving group for our nucleophile. That was our nucleophile. So this is called addition-elimination reactions because we essentially formed a tetrahedral intermediate, and then we eliminated our good leaving group to sort of substitute our nucleophile. You see that? Do you see that kind of chemistry?
Yeah, it all makes sense. I think the thing was just that, like, I'm so unfamiliar with them, and I never knew where to start. And I know that you give us like what we're supposed to be forming, but I also kind of never know like when to end, and I don't know. So it's kind of like the starting and the ending. Like I get what you're saying with the tetrahedral intermediate and like the proton shuffling and all that, but it's like.
So I will say, I don't think I'm ever going to give you a mechanism to do where I don't tell you what we start with and tell you what you end with. And when I was working with Skylar and Jimmy yesterday, it was, okay, what you need to do is look at bonds that are broken, which means electrons move there, or bonds that are formed, which means we need to move electrons to make those bonds. So identify those bonds that are breaking and bonds that are forming, and then show me a dance of electrons that are going to get you there. Okay, so I do give you, even on the mechanism you're going to see on your exam, I give you what you start with, I give you what you end with. Now, I don't give you structures for those molecules, but they are molecules that are sort of Gen Chem 1 like molecules that I'd expect you to be able to draw a structure from them, you know, based on functional groups that you know. Okay. And then the last little piece that we talked about with mechanism was the latest set of 4 reaction mechanisms that you've done, where X is not a good leaving group. If X is a hydrogen here, meaning you have aldehydes, or it's a carbon atom, an R group, meaning you have ketones, what you see is the nucleophilic attack and the formation of the tetrahedral intermediate. You do the proton reshuffling, but then you're done because you don't have a good leaving group that can leave. So let me just kind of come over here and we'll show an example of that. So let's look at reaction mechanism 4 for that. So this is going to be the formation of a hemiketal. So when I look at what happens here, and in this case, well, let's start up top here. This is a simpler scenario. Nucleophilic attack. So this is how I can quickly tell when I'm grading reaction mechanisms. I'm always going to see electrons like going in a flow. If I ever see 2 arrowheads coming together, or I see something, an arrow goes out into space or things like that, that's an immediate red flag to me that something's not right with the mechanism, right? So I usually see at least 2 arrows. So if I only see 1 arrow, I know somebody's missing an arrow, right? But I see nucleophilic attack, formation of this tetrahedral intermediate. We do some proton reshuffling here because otherwise this is still a decent leaving group. But here, if I wanted to reform this carbonyl, The only thing that could potentially leave, and it's not willing to leave right now because it's not protonated, is this guy, because I'm not going to break the carbon-carbon bond or that carbon-carbon bond. And if I did break this one, which is a possibility because all of these are reversible, all I do is get back to my starting material. Okay. But so take comfort in the fact that the mechanism that you're going to see is going to be one where you get structures of what you start with and what you need to get to. And so you'll know, and you can figure out, okay, what bonds are going to break, what bonds are going to form, and then use things. In my mechanisms early on here, I use water a lot as either, in this case, an acid or a base, but feel free to go ahead and use, for example, here, you could use BH+, and you could just use B here. Like I have here, up here, you could just use B as a base, and you could use BH+ as an acid. And I'm going to encourage people to start doing that more, because that's going to just get you into the mindset of thinking like, hey, I just need to have something that's a base over here in terms of an amino acid residue, or an acid over here for an amino acid residue. And that's going to help with our understanding when we look at enzyme active sites. Okay, so that's kind of a quick run through on mechanism. I will say, make sure that you know those, that last, let me go back to homework here. Where are we? Okay, so we went through, here's question 5 is a little bit more on thermodynamics. Question 5 is basically using your delta G equals delta H minus T delta S equation, and then using your delta G equals minus RT ln of K equation. So you need to know those two equations.
Yeah.
Okay, but doing some math with those. Question 6 has to do with equilibrium shifting. So that has to do just with some qualitative stuff there. Question 7 is kind of related to that. I know I've worked with a few people on question 7. The key here with this one, start by writing an equation that basically you're using tris, and tris is a weak acid. So write tris and then connect it to H+. And then it dissociates into tris plus H+. That's what a weak acid does. This is an important piece to it. It tells you delta H is a positive value. So Emily, I'm going to put you on the spot. Delta H is positive. Is that endothermic or exothermic?
Positive is endo, right?
Very good. Yep. Okay. So am I going to put heat on the right or the left side of that equation? It's endothermic.
If it's endothermic, that means it's coming in. Would it be the right side?
So you were right. You were right with what you said first. Endothermic means heat is coming in, which means it's a reactant.
Oh, okay. Okay.
Okay. So, and that's related to this question 6 that we have up here. Okay. This is an exothermic process. So for an exothermic process, that means we write heat as a product.
Okay.
Notice when I taught you in class sort of about this, and we talked about using an enthalpy parameter to tell us where we see heat. We're going to treat heat as a reagent. And a reagent does not imply whether it's a reactant or a product. So when heat is a reagent, it can either be a product, which is what we have with this problem, or it can be a reactant, which is what we have with problem 7. Does that make sense?
Okay. Yeah.
So, and when you treat heat as a reagent, the same sort of philosophy works. If we increase temperature, that means we're adding heat. If we decrease temperature, we're removing heat. So treat it just like you do these additions or removals. Okay. So use that to answer part A up here. And then down here, think about that equilibrium I just told you about writing, and see if you can explain why we have a pH shift when we change the temperature of our buffer. Okay. This problem is sort of related to a problem that you see on your test where you get some structures and you want to sort of think about ranking them in terms of solubility. With solubility, like dissolves like, okay? So if you want to dissolve something in water, you want to find the thing that is the most polar, so it has the most dipole-dipole interactions, maybe has the most charges, right? Think about your hierarchy of intermolecular forces. The more of those polar intermolecular forces you have, the more likely you are to dissolve in water, okay? So that's what homework problem 8 is basically using Wikipedia to look up the structures of these. I think there's 6 species that are there, all things that we're going to see throughout this course here. And then do your best to try to predict where they would fall solubility wise, and then look up their solubility values. You might need to do a little calculating to make sure that everything's in the same units. Some of them might be milligrams per liter, some of them might be grams per liter. So you need to have them in the same units so that you're sort of talking apples and apples. But see if your predictions were correct. So you won't get, and again, I do not grade homework for accuracy. I grade it for completion. Okay, so it's your job to do your best to get the most out of doing the homework, knowing that homework problems are related to the things you see on tests, but you're going to get credit for just completing. And then problem 9 is basically, let's see, it's going to be this piece. It is our, flipping back. I got to go a ways through here. Our blood buffering system. It is this slide. You want to be able to recreate. So let me flip back to this homework question. Write down the 3 equations we've discussed, the basic fuel metabolism equation. And I have this in quotes, the breathing/ventilation equation, you know, talking about what comes in and what goes out, and then the blood buffering equation. Okay. And basically talk about how they're going to be connected. Now, I will say, you're not going to recreate this whole slide on a quiz or on your exam question, but there are aspects of it I'm going to ask you to speak to. So the more that you can kind of recreate portions of this or understand how certain pieces of it talk to one another, that's going to get you through answering those questions.
There's a video on this slide, right?
Yep.
Okay,
So coming back here to show you where that stuff is under our learning units folder. We have my slow computer right now. Yep. So here's 3 videos that are important. So there's the blood buffering system video. And so with these, there's stuff that I had from previous years that walks through my slides that are already done.
Okay.
But one of the pieces of feedback I got from students last year was sometimes some of the more complex ones, it would be nice if I could watch you create them rather than talk about them from like just a static standpoint. Okay. And so that's what these ones are. I'm just going to kind of start it here maybe.
So this video.
So it literally walks through when we created this, because sometimes when you have these big ones like this, it's hard to understand what the story was when it's just all there at once.
Yeah.
So that's one that's there for that. I would make sure you know how to draw a reaction coordinate.
Okay.
Okay. So if you want to think or do something with reaction coordinates, here's a video for that here. I kind of do a real brief review of equilibrium and kinetics to start. And then I kind of walk through a generic drawing a generic reaction coordinate. You know, the parts that you're going to have there, what has to do with whether, how much and how fast. And then I go back through the ATP hydrolysis story. Okay. So, and then I already mentioned this one has to do with recreating this kind of slide on thermodynamics. So thinking about enthalpy, entropy, and free energy. Okay. And as I've been going through this with you, I am looking at, my key for the exam, and I have talked about everything that's on there.
Okay.
Questions?
I don't think so. I just need to look stuff over. Quick, what are your office hours on Thursday?
Well, because I'm in lab all day, I don't have office hours.
Okay.
And so it's not a bad, you can certainly ask, because I think we're going to have time Thursday in lab, because the intent is I'm going to go through a little bit in the beginning, kind of teaching you a few techie tools to sort of help with sharing your research. And then the goal is to give you guys time to finish up your data analysis lab, your lab math. And then if you wanted to work on anything with your boot camp lab, just so that you can basically get those close to finished, because they're all going to be due the following week. But you certainly can ask me questions on Thursday related to any of this content as well.
Okay.
And what was going on Thursday? I'm trying to think. My husband is leaving with David. They're flying out to go to Georgia. He has soccer game. My 12-year-old goes to Georgia, to Atlanta, to play soccer right now.
Me. I had tournaments in Vegas and Disney and everywhere, so I get it.
Yep, he's playing with an ECNL team right now. So
I was on ECNL, the Flash. I played for Flash for a little bit.
He's on the Flash right now. Yeah, he's playing Western New York Flash. So he's on. Go ahead.
I did DA, the Development Academy, for a couple years. That was my last couple years before I came to college.
Yeah. So I mean, it's not like all the time they're traveling across the country. Like this past weekend, I was in Pittsburgh with him for a game. But twice a year they play nationally. And if they do well here, they'll likely go to San Diego. It's like,
I went to San Diego.
Yeah. So my husband is not in love with flying. In 30 years together, we've flown once. And so I'm like, you're not driving to Georgia. No, we do not have time for this right now. And I'm grateful that we've had my in-laws have a ton of miles. So they got plane tickets, because otherwise this would have been like a $2,000 weekend. And it's just insane. So sorry, Adam, you're hearing a whole bunch of soccer stuff that's not related to biochemistry. But go ahead. Do you have any questions?
Not really anything specifically. I'm sort of in a similar position with the mechanisms, except a little bit more behind, the general ins and outs of it. I mean, I can study all the material that I have here, which is a lot with the slides you've given here, and I can look over the ones that I already have in my folder. So that should get me to a fairly good place. And I'll see if I can do office hours with you tomorrow and go over some homework stuff and things like that.
Yes. So regardless, so let's assume, because Adam had asked the question, he's like, what if Hearst Day is tomorrow? Will you still have office hours? Because they usually have good food on Hearst Day too. I think I might want to be there at lunchtime. And my challenge is that Charlotte has a vet appointment at 2, actually with Dr. Jones's wife. But I'm thinking maybe I'll bring Charlotte to school with me, since I don't technically have classes, and she can get some food, or I can get some food. She can hang out, and then I could be around for office hours. But if there's not Hearst Day tomorrow, I still have office hours from 12 until probably 1-ish. But if we do have classes and then I don't bring Charlotte in with me, that means I have to go home and get her to take her to her vet appointment. So I'll probably only be around from 12 to 1, but I'll definitely be around then, Adam.
If it is Hearst Day, how early do you think you'd be there? Just because we have a game at 1 and locker room at 11:30. So would you be there before then, or probably not?
I don't know. I just, yeah. I have to just sort out my home is a disaster right now, because we have not been home, like literally the piles of dishes and laundry. So it's like, oh my gosh, just having Hearst Day will allow me to maybe just try to get caught up on some household stuff. So I don't know. I don't know, but I will send out a message if I'm in my office and just make sure that you guys know that I'm around if you have questions.
Okay.
And I think with the exception of tomorrow, I'll be around in the evening if you have questions too. We can always do something like this. We can have like a little team session or something. Because Sam has a soccer game tomorrow night. But I think varsity plays at 6, so it's earlier. So I'll be home. It's a home game too, I'm pretty sure. Yeah, it's a home game. All right. Anything else? We're pretty good. I'm just starting to dip into the second hour and I didn't want to do too much of that.
I think I'll be good until I, start reviewing stuff and then more questions will pop up, but
Sounds good. But yeah, I think Thursday is an opportune time to probably try to handle some of those questions. I'm totally fine doing that on Thursday.
thank you so
All right.
much.
All right. We'll see ya.
Bye.
Bye.